The quest to discover extraterrestrial life has been a driving force in both scientific inquiry and popular imagination for centuries. This pursuit transcends the bounds of Earth, extending to our solar system and beyond, as we seek to answer one of humanity's most profound questions: are we alone in the universe? The search for life beyond Earth has evolved significantly over time. Initially, it was rooted in philosophical and theoretical discussions, but has now become a cornerstone of modern astrobiology, a field that integrates biology, astronomy, and geology. The discovery of extremophiles on Earth, organisms that thrive in environments once considered uninhabitable, has expanded our understanding of potential life-sustaining conditions. Modern efforts involve sophisticated telescopes scanning distant exoplanets for biosignatures, robotic missions exploring our solar system's planets and moons, and the analysis of meteorites for signs of past or present life. This endeavor is not just about finding aliens, it's about understanding the conditions that support life, the resilience of life in extreme environments, and the potential for habitability beyond our planet. Jupiter, the largest planet in our solar system, holds a unique position in the quest for extraterrestrial life. Its massive size, strong magnetic field, and numerous moons present an intriguing array of environments that could potentially harbor life. Jupiter is a gas giant, primarily composed of hydrogen and helium, with no solid surface. This composition and its immense atmospheric pressure make the planet itself an unlikely host for life as we know it. However, Jupiter's significance lies in its impact on the solar system. Its gravitational pull has influenced the orbit of other celestial bodies, potentially affecting the delivery of organic compounds to the inner planets, including Earth. Jupiter's magnetosphere, the largest structure in the solar system, offers a natural laboratory for studying the effects of intense radiation on planetary bodies and potential life forms. Moreover, Jupiter's diverse moons, especially Europa, Ganymede, and Callisto, have become prime candidates in the search for extraterrestrial life. These moons, with their subsurface oceans, offer an accessible model for studying the potential for life in extraterrestrial aquatic environments. Jupiter has always captured the human imagination with its prominent presence in the night sky. In ancient times, it was observed and revered by various cultures, often named after their chief deity. With the advent of telescopes, Jupiter revealed more of its secrets, from its swirling clouds to its four largest moons, known as the Galilean moons. The intrigue of Jupiter is not just its size and visibility, but the mysteries that it holds. Its Great Red Spot, a gigantic storm larger than Earth, has been raging for centuries, offering a glimpse into extreme weather phenomena. The planet's fast rotation, just under 10 hours for a full spin, and its complex cloud layers present a dynamic and ever-changing atmosphere that challenges our understanding of planetary atmospheres. The mystery extends to its potential role in the early solar system. Jupiter's formation and migration might have had significant impacts on the formation of other planets, including Earth. Understanding Jupiter's history is crucial to piecing together the solar system's evolutionary puzzle. Jupiter, a behemoth in our solar system, is a gas giant primarily composed of hydrogen and helium. Its massive size, over 1,300 times the volume of Earth, and significant mass, about 318 times that of Earth, make it a dominant gravitational force in the solar system. Jupiter's rapid rotation, completing a spin in just under 10 hours, causes a noticeable flattening at the poles and bulging at the equator, leading to unique atmospheric dynamics. Jupiter's atmosphere is a dense, turbulent mix of gases with striking visual patterns and colors. The upper atmosphere is dominated by hydrogen and helium, with traces of ammonia, methane, water vapor, and other compounds. These elements, under Jupiter's extreme pressure and temperature conditions, create a rich tapestry of cloud bands and storms. The most famous of these storms is the Great Red Spot, a vast anticyclonic storm larger than Earth, which has raged for centuries. The atmosphere's depth is a subject of ongoing research, with various layers exhibiting different compositions and dynamics. The visible cloud layer extends about 50 kilometers below the cloud tops, where pressure and temperatures increase dramatically. Beneath this visible layer, the atmosphere transitions into a region of hydrogen and helium that gradually becomes metallic due to extreme pressures, contributing to Jupiter's strong magnetic field. Jupiter's atmosphere also exhibits powerful winds, some reaching speeds of 360 kilometers per hour, and lightning is much more powerful than Earth's. These atmospheric characteristics challenge our understanding of planetary weather systems and provide valuable insights into the dynamics of gas giants. Jupiter's magnetic field is the strongest of any planet in the solar system, about 14 times stronger than Earth's. This immense magnetic field is generated by the movement of metallic hydrogen in Jupiter's interior. The field extends far into space, creating a vast magnetosphere that traps charged particles, including electrons and protons, forming intense radiation belts. This magnetosphere is so large that, if visible, it would appear several times the size of the full moon in Earth's sky. It has significant effects on Jupiter's environment, influencing its atmospheric dynamics and affecting its moons, especially those with subsurface oceans like Europa. Understanding Jupiter's magnetic field is crucial for planning missions to the Jovian system, as the intense radiation poses a significant challenge for spacecraft and potential life. Jupiter is accompanied by a diverse family of moons, with over 79 known satellites ranging from tiny moonlets to the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto. These moons present a wide array of geological and potentially biological environments. Io is the most volcanically active body in the solar system. Europa has a subsurface ocean that may harbor life. Ganymede is the largest moon in the solar system, with its own magnetic field. And Callisto is a heavily cratered world with signs of subsurface oceans. Jupiter's faint ring system, discovered in 1979 by the Voyager mission, consists mainly of dust particles. Unlike the prominent rings of Saturn, Jupiter's rings are composed of small, dark particles, making them difficult to observe. These rings are likely formed by dust kicked up by micrometeoroid impacts on the small moons within the ring system. Jupiter has been a subject of fascination since ancient times, observable to the naked eye and playing a significant role in various cultural mythologies. The advent of the telescope in the 17th century marked a turning point in our understanding of Jupiter. Galileo Galilei's discovery of the 4 largest moons of Jupiter in 1610 challenged the Earth-centric view of the universe and was a pivotal moment in the history of astronomy. Over the centuries, telescopic observations have revealed more details about Jupiter's atmosphere, its rapid rotation, and its complex system of moons and rings. These observations have not only provided insights into Jupiter itself, but also helped refine our understanding of planetary motion and the laws of physics. The search for life beyond Earth challenges us to redefine our concept of habitability. Traditionally, habitability was thought to be tied closely to Earth-like conditions, a planet with liquid water, an atmosphere, and a temperature range that supports life as we know it. However, recent discoveries in astrobiology have expanded this narrow view. Astrobiologists now consider a broader range of environments where life could potentially exist. This includes places with extreme temperatures, high radiation levels, or those lacking sunlight, like the subsurface oceans of icy moons. The discovery of extremophiles on Earth organisms thriving in environments once deemed inhospitable has been pivotal in this paradigm shift. It suggests that life could exist in a variety of forms and under a range of conditions, some of which may be found on other planets and moons in our solar system, including Jupiter and its moons. Extreme environments on Earth, such as deep-sea hydrothermal vents, high-altitude lakes, acidic hot springs, and the dry valleys of Antarctica, are home to extremophiles. These organisms have adapted to survive in conditions of extreme pressure, temperature, acidity, and radiation. Studying these extremophiles provides valuable insights into the potential forms and mechanisms of life in extraterrestrial environments. These Earth-based models help scientists hypothesize about life in space, particularly in environments like those on Jupiter's moons. For instance, the extremophiles in Earth's deep-sea vents offer a model for understanding potential life in the subsurface oceans of Europa. Similarly, organisms surviving in high radiation environments provide clues about how life might withstand the intense radiation around Jupiter. While Jupiter itself is unlikely to host life due to its extreme conditions, its atmosphere and the environments on its moons might support life forms. Theoretical models of life in Jupiter's atmosphere speculate about aerial microbes or plankton-like organisms. These hypothetical life forms could survive in the upper layers of the atmosphere, where pressure and temperature are less extreme. The concept of aerial life in Jupiter's upper atmosphere is based on the idea of organisms that could float or swim in dense atmospheric gases. These hypothetical life forms might resemble terrestrial plankton, surviving on chemical energy derived from Jupiter's atmospheric compounds. They would need to adapt to the planet's strong winds and radiation, possibly developing protective mechanisms or living within more stable atmospheric layers. Such life forms could have metabolisms based on chemicals available in Jupiter's atmosphere, like hydrogen, methane, and ammonia. They might form part of a complex ecosystem, with different species occupying various ecological niches, much like marine ecosystems on Earth. Microbial life in Jupiter's environment, if it exists, would likely be found on its moons, particularly Europa, Ganymede, and Callisto. These moons are thought to have subsurface oceans beneath their icy crusts, environments that could be hospitable to life. The hypothetical microbial life in these oceans might be similar to extremophiles on Earth, such as those found in Antarctic ice or deep-sea hydrothermal vents. These microbes might rely on chemosynthesis, using chemical reactions rather than photosynthesis to obtain energy. This is particularly relevant for environments like Europa's subsurface ocean, which is cut off from sunlight. The potential for hydrothermal vents on the ocean floor, as hypothesized for Europa, could provide the necessary energy and nutrients for such life forms. Jupiter's moons, Europa, Ganymede, and Callisto, are of particular interest in the search for extraterrestrial life. Europa is the prime candidate, with its subsurface ocean beneath a thick ice crust, which might harbor life in an environment similar to Earth's deep-sea hydrothermal vents. Ganymede, the largest moon in the solar system, also has a subsurface ocean and a thin oxygen atmosphere, making it an intriguing target for astrobiological research. Callisto, though less active geologically, is believed to have a subsurface saline ocean, expanding the potential habitable environments in the Jovian system. Europa, Ganymede, and Callisto, three of Jupiter's largest moons, represent key interests in the search for extraterrestrial life within the Jovian system. Each moon presents unique characteristics that fuel the curiosity of scientists and astrobiologists. Europa, with its smooth, icy surface crisscrossed by lines and cracks, hints at a dynamic internal life. Its subsurface ocean, potentially warmed by tidal heating due to gravitational interactions with Jupiter, could provide conditions suitable for life. This ocean, hidden beneath kilometers of ice, may contain more water than all of Earth's oceans combined, presenting an exciting possibility for aquatic life forms. Ganymede, the largest moon in the solar system, is unique for having its own magnetic field, suggesting a differentiated internal structure with a metallic core. Like Europa, Ganymede is believed to harbor a subsurface ocean, sandwiched between layers of ice. This environment could be another haven for life, potentially offering chemical nutrients and energy sources necessary for biological processes. Callisto, the outermost of the Galilean moons, appears heavily cratered and is the least geologically active of the three. However, it is also thought to possess a subsurface ocean. This moon's ancient surface, with fewer signs of internal activity, provides a contrast to Europa and Ganymede, offering a broader perspective on the conditions that may support extraterrestrial life in the Jovian system. The concept of subsurface oceans on Jupiter's moons has significantly expanded the search for extraterrestrial life. These oceans, protected from the harsh conditions of space by thick ice crusts, could provide stable environments for life. The key to these oceans' potential habitability lies in their composition, temperature, and the energy sources available for sustaining life. On Europa and Ganymede, the subsurface oceans are thought to be in contact with the moon's rocky mantles, allowing for potential chemical interactions that could provide energy and nutrients. This environment is reminiscent of Earth's deep-sea hydrothermal vents, where life thrives without sunlight, relying on chemosynthesis. The presence of liquid water, essential for all known forms of life, combined with a potential energy source, makes these oceans prime targets in the search for alien life. Callisto's ocean, while less studied, adds to the diversity of potentially habitable environments. The exploration of these oceans is not only about finding life, but also understanding the conditions that support it. which could redefine our concepts of where life can exist in the universe. Jupiter's moons, particularly Europa, Ganymede, and Callisto, play a crucial role in understanding the habitability of the Jovian system. While Jupiter itself is inhospitable, its moons offer a variety of environments where life could potentially exist. Studying these moons provides insights into the range of conditions under which life can survive and thrive. The investigation of subsurface oceans on these moons can shed light on the possibility of life in extreme and isolated environments. It also helps in understanding the dynamics of celestial bodies under the strong gravitational influence of a giant planet like Jupiter. The moon's geological activities, internal heating mechanisms, and interactions with Jupiter's magnetosphere are key factors in assessing their potential to support life. Exploring Jupiter and its moons presents significant technological and scientific challenges. The immense distance from Earth requires advanced propulsion and communication technologies for spacecraft. Jupiter's intense radiation environment poses a major threat to both spacecraft and potential biological studies. Protecting delicate instruments and ensuring the longevity of missions in such harsh conditions is a formidable engineering challenge. Scientifically, the complexity of Jupiter's atmosphere and the hidden nature of its moon's subsurface oceans create hurdles in obtaining direct evidence of conditions and potential life. Understanding the intricate interactions within the Jovian system, such as the effects of Jupiter's magnetic field on its moons, requires sophisticated instrumentation and comprehensive data analysis. Despite the challenges, the potential for groundbreaking discoveries fuels ambitious future missions to Jupiter and its moons. Proposed missions aim to further explore Europa's ocean, Ganymede's magnetic field, and the geological history of Callisto. These missions, involving orbiters, landers, and possibly subsurface probes, are designed to better understand the moon's environments and assess their potential for harboring life. Technological advancements in spacecraft design, propulsion, and communication will play a crucial role in these missions. In addition, developing innovative ways to penetrate the ice crusts and explore the subsurface oceans directly would mark a significant leap in extraterrestrial exploration. The discovery of life on Jupiter's moons would be a monumental achievement in human history, profoundly impacting our understanding of life in the universe. It would confirm that life can arise and persist in environments vastly different from those on Earth, potentially leading to a reevaluation of the criteria for habitable worlds. Such a discovery would also have philosophical implications, challenging our place in the universe and expanding our perspective on the diversity of life forms. It could catalyze further exploration and research, not just within our solar system, but also in the study of exoplanets and the broader search for extraterrestrial intelligence. Exploring Jupiter presents a multitude of technological and scientific challenges, primarily due to its extreme environment and great distance from Earth. The intense radiation belt surrounding Jupiter, created by its strong magnetic field, pose a significant risk to spacecraft electronics and instruments. This radiation can degrade components over time, challenging mission longevity and data integrity. Furthermore, Jupiter's immense distance from Earth, averaging about 778 million kilometers, complicates communication and increases travel time for spacecraft. This distance requires autonomous systems and robust engineering to ensure mission success in the event of communication delays or interruptions. Scientifically, deciphering the complex dynamics of Jupiter's atmosphere and magnetosphere is no small feat. The gas giant's weather systems, with their high-velocity winds, turbulent storms, and deep atmospheric layers, present a challenging environment for study. Additionally, understanding the internal structures of Jupiter and its moons, particularly their subsurface oceans, requires sophisticated instruments capable of penetrating and analyzing these hidden realms. The future of Jovian exploration is promising, with several missions planned or proposed to further investigate Jupiter and its moons. The primary focus of these missions is to explore the potential habitability of the Galilean moons, especially Europa, which is considered one of the most promising candidates for finding extraterrestrial life in our solar system. One of the most anticipated missions is NASA's Europa Clipper, slated for launch in the 2020s. This mission aims to conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean, assessing its habitability and paving the way for future landing missions. ESA's Jupiter Icy Moons Explorer, JUICE, is another ambitious mission, set to explore Ganymede, Europa, and Callisto, focusing on their potential as habitable worlds. Additionally, there are proposals for more advanced missions, including landers or probes that could penetrate the ice crusts of these moons and directly sample the subsurface oceans. These missions would require significant advancements in technology, particularly in ice-penetrating radar, robotic drilling, and miniaturized life detection instruments. The discovery of life on Jupiter's moons would be a watershed moment in our understanding of the universe. It would not only affirm that life can exist in environments vastly different from Earth, but also potentially offer insights into the diversity and resilience of life forms. Such a discovery would have profound implications for our understanding of biology, evolution, and the conditions necessary for life. It would also raise philosophical questions about humanity's place in the cosmos and the uniqueness of life on Earth. The potential for a second independent genesis of life within our own solar system would have far-reaching consequences for our search for life in the universe, suggesting that life might be more common than previously thought. Jupiter, with its complex system of moons, offers a unique laboratory for studying the potential for life in the universe. The diverse environments found on its moons, from subsurface oceans to extreme radiation zones, provide a microcosm for understanding how life might arise and survive under various conditions. Studying Jupiter and its moons can help refine our models of planetary formation and evolution, offering insights into the habitability of other planetary systems. Jupiter's influence on the solar system, from its role in shaping the orbits of other planets, to its potential impact on the delivery of water and organic materials to the inner solar system, is crucial in understanding the conditions that led to the emergence of life on Earth. The lessons learned from exploring the Jovian system could be applied to exoplanet research, particularly in identifying and characterizing planets and moons that could host life. Understanding the range of environments where life could potentially exist broadens the scope of our search for extraterrestrial life, making Jupiter a key piece in the puzzle of life in the universe. Discovering life on Jupiter's moons would revolutionize our understanding of biology. It would challenge our Earth-centric view of life, potentially introducing new biological processes, chemistries, or forms of life. Studying extraterrestrial life forms could reveal alternative biochemistries, expanding our knowledge of the building blocks and mechanisms of life. Jupiter, with its diverse and extreme environments, offers valuable insights into the potential for life in the universe. Its large system of moons, each with unique geological and chemical characteristics, serves as a miniature laboratory for studying various astrobiological possibilities. For instance, Europa's subsurface ocean could mirror conditions on distant exoplanets, providing a model for life existing in hidden aquatic environments. Similarly, Ganymede's internal ocean and magnetic field could offer clues about the interactions between planetary magnetospheres and habitability. Exploring Jupiter and its moons helps refine our understanding of where and how to look for life beyond Earth. It challenges the traditional view of life requiring Earth-like conditions, expanding the search to include worlds with different atmospheres, temperatures, and chemical compositions. Jupiter's system thus contributes significantly to the broader astronomical effort to identify exoplanets and exomoons with conditions conducive to life. The potential discovery of life in the Jovian system would have profound implications for biology. It would challenge our current understanding of life's fundamental requirements and potentially introduce new biological processes. For example, life forms adapted to the extreme conditions on Europa or Ganymede could reveal alternative metabolic pathways or biochemistries, expanding our knowledge of life's diversity. Such discoveries could also provide valuable insights into the origins and evolution of life. Understanding how life might develop in environments vastly different from Earth could help answer fundamental questions about the nature of life itself. This knowledge would not only enrich biological science, but also guide our search for life in the cosmos, informing the criteria we use to assess the habitability of other worlds. The discovery of extraterrestrial life, particularly in a place as close as Jupiter's moons, would have far-reaching philosophical and cultural implications. It would profoundly affect our understanding of our place in the universe and challenge long-held beliefs about human uniqueness and the centrality of Earth in the cosmic scheme. Such a discovery could spark a new era of existential reflection and philosophical inquiry, prompting questions about the nature of life, consciousness, and the universe. It could also influence cultural narratives, art, religion, and ethics, reshaping our collective worldview and our perceptions of life, both on Earth and beyond. The exploration of Jupiter and its moons offers exciting prospects for understanding the potential for life in our solar system. The gas giant's extreme environment, while inhospitable, provides a backdrop against which the moon's more temperate conditions stand out. Europa, Ganymede, and Callisto, with their subsurface oceans and unique geologies, present plausible locations for life beyond Earth. The study of these moons, particularly their potential for harboring life in extreme conditions, is crucial in expanding our understanding of life's diversity and resilience. The future of Jovian exploration is bright, with several missions planned or proposed to delve deeper into the mysteries of Jupiter and its moons. These missions aim to explore the subsurface oceans of Europa and Ganymede, investigate the complex magnetic environment of Jupiter, and understand the geological history of Callisto. Advancements in technology, particularly in spacecraft design, propulsion, and instrumentation, will play a critical role in these endeavors. The continued exploration of Jupiter's system is not just about finding life, but also about understanding the processes that govern planetary systems and the conditions conducive to life. These missions will contribute significantly to our knowledge of the solar system and the broader universe, guiding future explorations and searches for extraterrestrial life. The search for life beyond Earth, particularly in the Jovian system, represents one of the most profound scientific endeavors of our time. It challenges us to rethink our place in the universe and expands our understanding of the possibilities of life. The study of Jupiter and its moons is a crucial step in this journey, offering a window into the diverse and extreme conditions under which life could exist. This exploration not only enhances our scientific knowledge, but also enriches our cultural and philosophical perspectives. It reminds us of the vastness of the universe and the potential for life in unexpected places. As we continue to explore Jupiter and beyond, we open ourselves to the possibilities of new discoveries, new understandings, and a deeper appreciation of the marvels of the cosmos. The potential for life on Jupiter, or more accurately, within its moon system, represents a paradigm shift in our understanding of life in the universe. Jupiter itself, a vast gas giant with extreme pressures and temperatures, is not a viable candidate for life as we know it. However, its moons, particularly Europa, Ganymede, and Callisto, offer intriguing possibilities. These moons harbor subsurface oceans beneath icy crusts, creating environments that might be conducive to life. Europa, with its geologically young surface and evidence of a liquid ocean beneath its icy shell, is a prime candidate in this search. The presence of a salty ocean, possibly in contact with a rocky mantle, creates the potential for hydrothermal activity similar to that on Earth, which could provide the energy and nutrients necessary for life. Ganymede's magnetic field and its own subsurface ocean further expand the potential habitable zones within the Jovian system. Callisto's age and heavily cratered surface provide a contrast, offering insights into the evolution of potentially habitable environments. While we have no direct evidence of life on these moons, the conditions present there, liquid water, chemical diversity, and energy sources, align with the key ingredients required for life. The exploration of these moons not only aims to find life, but also to understand the conditions under which life can exist, broadening our perspective on habitability in the universe. The future of Jovian exploration is poised at an exciting frontier, with several missions planned and proposed that aim to unravel the mysteries of Jupiter and its moons. These endeavors will not only seek to confirm the existence of subsurface oceans, but also to understand the geophysical processes that maintain these environments and assess their potential for supporting life. NASA's Europa Clipper mission, slated for launch in the 2020s, is set to perform detailed reconnaissance of Europa's ice shell and underlying ocean. Similarly, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, is scheduled to conduct extensive observations of Ganymede, Europa, and Callisto. These missions will provide critical data on the moon's surface compositions, internal structures, and interaction with Jupiter's magnetosphere. Advanced technologies in spacecraft design, propulsion, and communications are essential for these missions, given the challenges posed by the distance to Jupiter and its intense radiation environment. Innovations in ice-penetrating radar and submersible probes could eventually allow us to explore these moons' subsurface oceans directly, a feat that would mark a significant milestone in planetary science and astrobiology. The search for life beyond Earth, particularly in the Jovian system, is a quest that goes beyond scientific curiosity. It touches upon some of the most fundamental questions about our existence. Are we alone in the universe? What forms can life take in environments vastly different from our own? The potential discovery of life on Jupiter's moons would not only be a monumental scientific achievement, but also a profound philosophical revelation. This endeavor embodies the spirit of exploration and the human desire to understand our place in the cosmos. It encourages us to look beyond our planet and consider the possibilities of life under a variety of cosmic conditions. Whether we find life in the Jovian system or not, the journey of exploration will undoubtedly enrich our understanding of the universe and our role within it. The exploration of Jupiter and its moons is a reminder of the vastness of space and the endless possibilities it holds. It challenges us to expand our perspectives, to think creatively about life and its myriad forms, and to continue our quest for knowledge with an open mind and a sense of wonder.